Hello, and thank you for joining me on this gentle journey. Tonight, we will slowly drift into the quiet brilliance of white dwarfs. Imagine floating through the vastness of space, surrounded by countless stars, as your gaze rests upon these dense stellar remnants, glowing faintly against the infinite darkness. Each white dwarf carries a story from billions of years past. A core once part of a massive star, now cooled and crystallized, holding secrets of gravity and nuclear fusion in its compact form. Picture their subtle light twinkling softly, a serene cosmic hum filling the void, while you allow your mind to wander among their icy surfaces and faint luminosity. If you enjoy these relaxing moments, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, just breathe. Let your body relax, release any tension, and allow your mind to drift. Let's begin. The life of a white dwarf begins long after a star has exhausted its nuclear fuel, leaving behind a dense core that glows faintly with residual heat. Though no longer sustaining fusion, the star's compressed matter radiates light across space, a subtle whisper of its former brilliance, revealing the intricate balance between gravity and quantum forces that hold it from collapsing further. Beneath its surface, electrons are packed so tightly that they create a quantum pressure known as electron degeneracy, a force that counteracts the relentless pull of gravity. This invisible resistance allows the star to maintain its shape, giving rise to a sphere of unimaginable density where a teaspoonful of matter could weigh tons on Earth. The cooling of a white dwarf is a slow, patient process, spanning billions of years. Its luminosity gradually diminishes, and the star fades into a pale, ghostly glow that drifts across the cosmos. Observing this dim light offers astronomers a glimpse into the ancient life of stars and the long history of the universe. After shedding its outer envelope, the remnant star's core remains intensely hot, radiating energy across ultraviolet and visible wavelengths. Its compact size concentrates mass into a small volume, creating surface gravity thousands of times stronger than Earth's, bending light, compressing matter, and shaping an environment where ordinary atomic behavior gives way to exotic, extreme physics. Some residue host thin disks of dust and gas from tidally disrupted asteroids or minor planets. These accretion disks glow faintly in infrared and occasionally produce spectral lines of heavier elements, revealing evidence of destroyed planetary systems and offering insight into the gravitational influence of ultra-dense stellar cores. White dwarfs vary widely in size and mass, typically comparable to Earth in diameter, but packing mass similar to that of the Sun. This extraordinary density creates a gravitational field so intense that the star subtly warps the light passing near it, bending photons in a cosmic ballet of relativity. The cores of these stars are composed primarily of carbon and oxygen, remnants of fusion processes that once fueled the star's brilliance. In some rarer cases, white dwarfs may have helium cores, or even oxygen neon magnesium cores, reflecting the diversity of stellar evolution paths across different masses and compositions. Rarely, stellar remains may retain trace amounts of lithium or beryllium from their progenitor stars. Detecting these elements challenges models of stellar evolution, revealing hidden clues about nuclear fusion history and the subtle chemical legacy that survives the death of a star. Magnetic fields in white dwarfs can reach astonishing strengths, millions of times stronger than the strongest magnets on Earth. These invisible forces can shape the star's atmosphere, influence particle motion, and in binary systems, guide streams of matter spiraling onto the white dwarf, generating delicate arcs of radiation, visible across vast interstellar distances. A few rapidly spinning stellar remnants complete rotations in mere minutes, conserving angular momentum from their progenitor stars. These rotations generate equatorial bulges, redistribute heat, and interact with magnetic fields to produce small but measurable variations in brightness that can be detected across astronomical distances. Magnetic fields, sometimes exceeding 1 billion Gauss, shape the surrounding plasma and guide infalling material along polar arcs. The interaction of strong magnetism and rotation produces luminous spots and subtle radiation variations, revealing complex physical dynamics that illuminate how matter behaves under forces far stronger than anything on Earth. Some white dwarfs rotate with remarkable speed, completing a full rotation in minutes or hours. This spin, a remnant of the star's original angular momentum, interacts with the magnetic field to create subtle variations in emitted light, a faint celestial heartbeat that allows astronomers to measure and study these ancient objects. Strong magnetic fields can trap ionized particles in loops above the surface, producing localized emissions analogous to planetary auroras. These bright spots rotate with the star, offering periodic signatures that illuminate the complex interplay of magnetism and surface activity in an ultra-dense, high-gravity environment. In some cases, tidal forces from a close companion can disrupt orbiting planets, pulverizing them into debris. This material forms transient rings or disks, producing infrared signatures that reveal the violent gravitational influence of dense cores on surviving planetary systems. Subtle shifts in spectral lines reveal rotational velocity and surface composition, allowing astronomers to deduce internal structure without direct observation. These measurements uncover rotational dynamics, crystallization patterns, and the extent of degenerate matter, offering a non-invasive window into stellar interiors. In binary systems, white dwarfs can accrete matter from a companion star, slowly gaining mass and occasionally triggering dramatic outbursts known as novae. These explosions release bursts of energy that briefly illuminate the surrounding space, painting a fleeting spectacle that contrasts with the star's otherwise patient, enduring glow. Crystallization within the cores of older white dwarfs transforms the matter into a solid, diamond-like lattice. This process, occurring over billions of years, releases latent heat and subtly slows the cooling of the star, turning the remnant into a cosmic jewel, a frozen testament to the passage of time in the galaxy. Crystallization occurs in the cores of older leftovers, rearranging carbon and oxygen atoms into rigid lattice structures. This transformation releases latent heat, delaying cooling and turning the star into a solid, diamond-like object that could persist for trillions of years, standing as a frozen monument to stellar evolution. When paired with a close companion, these remains can accrete hydrogen or helium-rich material. Accumulated layers may ignite in brief, luminous outbursts known as novae, temporarily illuminating the system and providing a visual record of the delicate interplay between accreted matter, nuclear ignition, and gravitational forces. Some emit X-rays due to high-energy accretion events, with matter heated to millions of degrees as it spirals inward. These emissions allow astronomers to probe extreme conditions unattainable on Earth, revealing the intense energy transformations that occur in compact stellar environments. Some of the nearest white dwarfs to Earth, like Sirius B, appear as faint points of light near their brighter companion stars. Despite their proximity, these stars are often invisible to the naked eye, requiring telescopes to reveal the subtle glimmer of their dense, ancient remnants against the backdrop of the night sky. White dwarfs serve as cosmic chronometers, helping astronomers estimate the age of star clusters and even the galaxy itself. By measuring their temperature and luminosity, scientists can calculate how long these stars have been cooling, providing a unique window into the timeline of stellar and galactic evolution. Theoretical models predict that collisions between dense cores and asteroids could generate high-energy flares visible across light years. Observing these events could offer evidence of surviving planetary debris interacting with the remnants' extreme gravitational field, linking stellar death to ongoing material evolution. Some compact stars cool slowly enough to remain visible for trillions of years in theory. These ultra-long-lived objects act as cosmic timekeepers, preserving a record of stellar evolution while silently influencing the distribution of matter in their galactic neighborhoods. White dwarfs sometimes exhibit pulsations, rhythmic expansions and contractions that cause subtle variations in brightness. These oscillations, like the resonant hum of a celestial instrument, offer clues about the star's internal structure, composition, and thermal state, turning each flicker into a story about the physics hidden beneath the surface. Despite their diminutive size, white dwarfs can exert extreme gravitational lensing effects, bending the light from background stars and galaxies. Observing these distortions allows astronomers to map the invisible mass of the star and explore the fabric of space-time itself, revealing both the power and subtlety of these compact remnants. Pulsations of varying periods ripple through their interiors, causing periodic brightness fluctuations. These oscillations act as natural seismographs, offering insight into core composition, thermal gradients, and the onset of crystallization, allowing scientists to study internal structures with precision akin to analyzing the Earth's interior using earthquakes. Certain remnants act as gravitational lenses, subtly bending light from background stars. Observing these distortions provides measurements of mass and tests of general relativity, demonstrating the profound effects that highly concentrated matter has on space-time, and offering a window into phenomena that would otherwise remain invisible. Temperature gradients across the surface can vary due to rotation, magnetic activity, or accreted material. Hotspots may emerge near magnetic poles, emitting more intensely than surrounding areas, creating subtle fluctuations in light that serve as cosmic fingerprints of the star's magnetic and rotational characteristics. The atmosphere of a white dwarf is often thin and composed mostly of hydrogen or helium. Spectroscopic studies reveal traces of heavier elements, hinting at interactions with surrounding debris, the remnants of planetary systems, or accreted matter from companion stars, painting a delicate portrait of past stellar environments. White dwarfs can be found throughout the galaxy, from dense star clusters to the isolated reaches of interstellar space. Their widespread presence acts as a map of stellar evolution, marking where stars once lived and died, leaving behind glowing embers that trace the history of the cosmos. The first white dwarf ever discovered, 40 Eridani b, was identified in the 19th century through its faint luminosity and high density. Observations of such stars challenged early notions of matter and gravity, revealing the extraordinary physics at work in these compact objects far beyond everyday experience. The mass-radius relationship in these objects is unusual. Adding mass reduces radius due to electron degeneracy pressure. Observations of compact stars confirm these predictions, providing empirical evidence for quantum mechanical effects acting at macroscopic, astrophysical scales and illustrating how extreme physics governs the cosmos. Remnants in globular clusters trace stellar history, revealing the ages and composition of ancient populations. By studying luminosity, temperature, and spectral features, astronomers reconstruct timelines of star formation, galactic evolution, and chemical enrichment in environments where gravity and density influence stellar interactions. Surface gravity is intense enough to compress atmospheric layers into a thin shell. This concentration of matter affects atomic transitions, pressure broadening, and absorption lines in spectra, offering scientists an extraordinary laboratory to study matter under conditions vastly different from those found on planets or in typical stars. Some white dwarfs emit X-rays, particularly when accreting matter from a companion. This high-energy radiation originates from matter heated to millions of degrees as it falls onto the star, offering astronomers a window into extreme physics that cannot be observed in cooler, more quiescent stellar remnants. White dwarfs play a crucial role in cosmic alchemy, as Type 1 supernovae arise when a white dwarf reaches critical mass. These explosions produce heavy elements like iron and nickel and serve as standard candles for measuring cosmic distances, linking the lives of these compact stars to the grand scale of the universe. Accretion-induced magnetic phenomena sometimes produce bursts resembling miniature solar flares. Charged particles accelerated along magnetic field lines impact localized regions, heating the surface and generating transient light emissions that reveal the intensity and structure of magnetic fields on compact stellar residue. Observations of remnants in different galactic populations reveal variations in mass distribution, rotation rates, and atmospheric composition. These differences reflect the progenitor star's environments, allowing researchers to trace the influence of metallicity, formation epoch, and local gravitational interactions on compact stellar evolution. Some stellar cores host thin helium atmospheres overlaying carbon-oxygen interiors. Studying the spectral transitions between layers provides insight into stratification, chemical differentiation, and residual fusion processes, highlighting how even ultra-dense leftovers retain a record of their progenitor star's internal dynamics. The cooling rate slows as crystallization releases latent energy, allowing remnants to retain observable luminosity longer than predicted by simple blackbody models. This extended glow offers a method to date ancient stars and reconstruct the evolutionary timeline of stellar populations in clusters and the galactic halo. Infrared observations can detect faint circumstellar dust from disrupted planetary bodies. The thermal glow of these disks provides indirect evidence of past planetary systems and highlights how gravitational forces continue to shape the environment around dense stellar cores long after nuclear fusion ceases. Pulsar-like beams occasionally arise when magnetic fields channel charged particles along rotation axes. These concentrated emissions sweep across space, creating periodic signals detectable from Earth and revealing the extreme interplay of magnetism, rotation, and ultra-dense matter in a celestial laboratory that challenges terrestrial understanding. The surface gravity of a white dwarf is immense, thousands of times stronger than Earth's. This gravity shapes the star's atmosphere, compresses matter into ultra-dense layers, and affects the behavior of atoms and light in ways that stretch the imagination and reveal the extraordinary extremes possible in the universe. When a star sheds its outer layers near the end of its life, it often creates a planetary nebula, leaving a white dwarf at the center. The exposed core glows fiercely against the surrounding gas, a fragile beacon of dense matter that compresses solar mass into a sphere no larger than Earth's diameter, revealing the stark contrast between immense gravity and faint luminosity. Remnants in globular clusters serve as age calibrators. Their luminosity distribution and temperature provide a record of cluster evolution, chemical enrichment, and the timing of star formation events, linking the physical properties of dense cores to the broader narrative of galactic history. Occasionally, high-speed remnants move through interstellar space after gravitational interactions, carrying with them debris from disrupted planetary systems. Observing their trajectories helps map galactic kinematics, population dynamics, and the influence of gravitational encounters over billions of years. Strong magnetic fields may generate cyclotron radiation, producing narrow spectral features in opticals or infrared bands. These emissions allow astronomers to reconstruct magnetic topology, field strength, and surface structure, offering a glimpse of how extreme magnetism shapes observable properties in ultra-dense stars. Layers of helium or hydrogen floating atop the white dwarf's core can interact with trace-heavier elements, creating subtle spectral fingerprints. These chemical signatures allow astronomers to reconstruct the star's evolutionary history, trace accretion events, and identify remnants of planetary material, painting a vivid narrative of matter cycling and stellar legacy across cosmic timescales. Gravity on a white dwarf's surface is so strong that it compresses atoms to extreme densities, shortening the distance between nuclei to mere fractions of their earthly counterparts. This compression affects the behavior of light and matter alike, producing spectral shifts and unusual pressure-broadened lines that offer glimpses into exotic conditions unattainable in terrestrial laboratories. White dwarfs can form in binary systems, where two stars of moderate mass interact, exchanging mass or evolving asymmetrically. In these scenarios, the compact star may siphon material from its companion, a delicate gravitational tug that subtly alters orbital paths and can set the stage for rare, high-energy, astronomical phenomena visible across light years. Rapid rotation can distort the shape, producing equatorial bulges and subtly altering gravitational acceleration across the surface. These deformations influence atmospheric dynamics and light emission, offering observable evidence of how angular momentum interacts with ultra-dense, degenerate matter. Spectral analysis sometimes detects metals like calcium or iron in their atmospheres. These elements usually originate from accreted debris, providing evidence of destroyed planets or asteroids, and revealing the remnants' gravitational ability to capture and process material from their surroundings. Some white dwarfs are enveloped in faint disks of gas or dust, remnants of former planetary systems, or captured material from companion stars. Observing these disks reveals clues about gravitational interactions, angular momentum transfer, and the long-term survival of matter in the intense environment surrounding ultra-dense stellar cores. Strong magnetic fields in certain white dwarfs can redirect accreting matter along polar funnels, causing bright hotspots at the star's magnetic poles. These localized emissions can flicker and pulse, producing distinct light signatures that allow astronomers to map magnetic structures and rotational periods in unprecedented detail. The interplay between rotation and magnetic field strength influences the stability of a white dwarf's atmosphere. Rapidly spinning stars can exhibit equatorial bulges, subtle variations in brightness, and complex surface dynamics that reveal the interplay between centrifugal forces and the gravitational pull of ultra-dense matter. White dwarfs often mark the endpoints of stars up to 8 solar masses. Stars more massive than this tend to collapse into neutron stars or black holes, making white dwarfs both common and critical in understanding the diversity of stellar evolution pathways within our galaxy and beyond. Luminosity in white dwarfs decreases over time as thermal energy radiates into space. Despite the gradual dimming, some younger white dwarfs shine with temperatures exceeding 100,000, producing intense ultraviolet radiation that can ionize surrounding gas, illuminating nearby nebulae in ghostly blue and violet tones, a testament to their enduring energy output. Type 1. A supernovae arise when a white dwarf in a binary system approaches the Chandrasekhar limit, detonating in a runaway thermonuclear explosion. These events release immense amounts of light and forge heavy elements such as iron and nickel, seeding galaxies with material essential for planetary formation and the chemical evolution of life-supporting environments. Binary interactions can lead to unusual phenomena such as dwarf novae, where the white dwarf accretes matter episodically. These temporary outbursts emit bursts of light that illuminate the surrounding accretion disk, offering a transient but vivid glimpse into the otherwise stable and slow evolving life of the compact star. Some white dwarfs exhibit pulsation periods spanning minutes to hours, reflecting resonances within the stellar interior. These pulsations allow astronomers to perform astroseismology, using surface brightness variations to probe core composition, layer thickness, and crystallization patterns, revealing details hidden beneath the glowing exterior. Theoretical models suggest that as white dwarfs cool, carbon and oxygen in their cores can form crystalline lattices. This crystallization releases latent heat, subtly prolonging the cooling timeline, and transforms the star into a solid, diamond-like object that could survive for trillions of years, embodying the physical extremes of dense matter in the universe. Some white dwarfs are part of triple star systems, creating complex gravitational interactions. The presence of a third body can induce orbital eccentricities, trigger accretion events, or even eject one of the stars from the system, illustrating the dynamic and interconnected nature of stellar remnants in multi-star environments. High-precision measurements of white dwarf masses and radii confirm predictions of the mass-radius relationship, where increasing mass leads to smaller size due to electron degeneracy pressure. Observing these correlations validates decades of quantum physics applied on cosmic scales, linking the behavior of ultra-dense matter to fundamental physical laws. Infrared surveys detect cold, slowly cooling remnants at the faintest luminosities. These stars emit primarily in longer wavelengths, revealing ultra-aged cores whose residual energy is dispersed across the galaxy, providing vital clues about the longevity and late-stage thermal evolution of compact stellar objects. Some compact stars in binary systems emit pulsed X-rays as accreted material follows magnetic field lines to hotspots on the surface. These high-energy beams reveal the intensity of magnetic fields and the dynamics of material in extreme gravitational environments, offering a natural laboratory for studying plasma physics. Chemical signatures in the atmosphere often indicate accretion of minor planetary bodies. Elements such as silicon, iron, and magnesium provide a fossil record of orbital debris, enabling astronomers to reconstruct the composition of long-destroyed planetary systems and the impact of gravitational forces over billions of years. White dwarfs have been observed to pollute with heavy elements from disrupted minor planets or asteroid belts. The infall of this material onto the surface offers a rare window into planetary systems long destroyed, enabling astronomers to reconstruct the architecture of distant solar systems through subtle chemical signatures. The faintest white dwarfs detected emit light comparable to or less than that of Earth's moon, making them challenging targets even with powerful telescopes. These ultra-cool remnants represent the final stages of stellar evolution, where the star has radiated away most of its thermal energy but continues to exist as a dense, solidified core. By tracing the motions of white dwarfs through the Milky Way, astronomers can reconstruct galactic dynamics. These stars often move with high velocities due to gravitational interactions over billions of years, serving as markers for population age, galactic structure, and the history of past star-forming regions. Remnants of stellar cores can exhibit subtle luminosity variations due to changes in surface composition, rotation, or magnetic field geometry. These variations produce faint flickers that travel across light years, allowing astronomers to interpret the hidden physical mechanisms shaping dense matter and offering a glimpse into extreme stellar environments beyond conventional observation. High-energy particles trapped along magnetic field lines can create small auroral-like emissions at the poles, producing soft glows that fluctuate with rotation. These features reveal the interplay between charged particles, magnetism, and ultra-dense matter, offering a visual signature of phenomena that bridge astrophysics and quantum mechanics. The retention of angular momentum from progenitor stars influences rotational speed, surface flattening, and magnetic alignment. Observing these characteristics allows scientists to reconstruct the prior evolution of the star, providing insight into the conservation of momentum in compact, degenerate stellar objects across billions of years. Some display spectral lines shifted by gravitational redshift as light climbs from the intense gravitational well. These shifts provide direct evidence of the extreme curvature of space-time near the surface, allowing verification of relativistic predictions and offering a rare opportunity to measure gravity under conditions far beyond terrestrial laboratories. Ultraviolet observations reveal that young stellar remnants can outshine the Sun despite their tiny size, radiating intense energy from residual heat. This emission illuminates surrounding gas, ionizing nebulae, and highlighting structures that serve as historical records of the progenitor star's final activity. The remains located in star clusters often serve as age benchmarks. Comparing their luminosities and temperatures across a cluster allows astronomers to trace the chronological sequence of star formation, linking individual stellar evolution to broader galactic history and the chemical enrichment of their environment. Some remnants rotate so rapidly that centrifugal forces create equatorial bulges, altering surface gravity and thermal distribution. These shape changes impact atmospheric structure and light emission patterns, providing observational evidence of extreme rotation and the delicate equilibrium between gravity and electron degeneracy pressure. Interactions with binary companions can produce dwarf nova events, where accumulated material ignites briefly, emitting bursts of light that illuminate nearby space. These eruptions demonstrate the delicate balance between accreted matter, surface temperature, and degenerate matter, revealing the dynamic behavior of compact stars over time. The extreme density of these objects compresses matter to a state where electrons are forced into higher energy levels, generating electron degeneracy pressure. This quantum mechanical effect counteracts gravitational collapse, illustrating how fundamental physics governs the structure of objects far beyond the scale of ordinary stars. Crystallization of the carbon-oxygen core occurs over billions of years, gradually transforming liquid-like interiors into solid lattices. This rearrangement releases latent heat, prolonging thermal emission and producing a remarkably long-lived remnant that preserves the physical record of its progenitor star in solid form. Observing cooling rates across a population allows estimation of their ages, linking thermal evolution to the history of the galaxy. This methodology provides a chronometer for stellar populations and contributes to understanding the timeline of star formation, chemical enrichment, and dynamical interactions over cosmic timescales. Some rotate at astonishing speeds, with angular momentum concentrated from earlier evolutionary stages. This rotation shapes magnetic field alignment, atmospheric distribution, and surface temperature variations, offering measurable effects that provide insight into the conservation of momentum and its influence on stellar structure. Interactions between compact remnants and close companions may trigger rare supernovae or create exotic stars. These events reveal the diversity of outcomes possible in binary systems and underscore how gravitational forces, mass transfer, and stellar evolution converge to shape the most extreme objects in the cosmos. Stellar remnants in dense galactic regions often interact gravitationally with nearby stars, causing subtle orbital shifts and tidal distortions. These encounters can eject material, trigger accretion events, or alter rotational dynamics, illustrating how compact cores remain dynamically active long after nuclear fusion ceases, quietly shaping their surroundings over billions of years. Occasionally, planetary bodies survive the death of their host star and orbit these dense cores. Observations of transits or spectral absorption reveal fragments of exoplanets, suggesting that debris from ancient planetary systems continues to circle compact remnants, offering a rare glimpse into the endurance of planetary architecture under extreme gravitational forces. Spectral studies sometimes detect helium-dominated atmospheres with traces of heavier elements, indicating either residual primordial layers or material accreted from circumstellar debris. This chemical fingerprint allows researchers to reconstruct the evolutionary history, revealing the long-term effects of gravity, radiation, and matter in full on ultra-dense, Stars. The surface layers can emit weak but persistent ultraviolet radiation, ionizing surrounding gas and shaping miniature nebulae. These illuminated clouds highlight past stellar activity, offering observers a natural laboratory to study radiation-matter interactions in extreme gravity, where photons escape slowly from the dense, compact surface. Some remnants in binary systems generate periodic X-ray bursts as accreted material impacts localized hotspots. These energetic flares produce observable variations in luminosity and reveal how magnetism, rotation, and surface composition interact, providing a window into physics under conditions far beyond those found in ordinary stars. Rapid rotation combined with strong magnetism can create surface temperature inhomogeneities, producing bands or spots of enhanced luminosity. Observing these patterns allows scientists to infer magnetic field geometry, rotational orientation, and energy transport, revealing how compact stars maintain complex surface structures despite extreme densities. The crystallization of carbon and oxygen within the core slowly releases latent heat, providing a subtle energy source that delays cooling. Over billions of years, this transformation converts a fluid-like interior into a solid lattice, preserving a detailed physical record of prior nuclear fusion and stellar evolution. Accretion from binary companions occasionally triggers thermonuclear flashes on the surface. These transient phenomena illuminate surrounding matter briefly, showcasing the delicate balance between mass accumulation, ignition thresholds, and surface gravity, and providing observable evidence of how compact stars interact dynamically with nearby stellar neighbors. Some remnants are located in isolated regions of space, far from stellar clusters. Despite their seclusion, they continue to emit residual thermal radiation, serving as silent beacons that trace the life cycle of mid-sized stars and act as markers of galactic history, even in the loneliest corners of the cosmos. Stellar leftovers influence surrounding planetary debris, gradually accreting dust and minor bodies. The resulting metallic contamination in the atmosphere provides direct evidence of past planetary systems, offering insight into long-term orbital evolution, tidal interactions, and the fate of exoplanetary material in high-gravity environments. Pulsations observed in these stars reveal core structure, layer thickness, and temperature gradients. By analyzing periodic brightness variations, astronomers perform a form of stellar seismology, using the light signatures to map internal composition and crystallization patterns without direct observation of the dense interior. When residing in multiple star systems, gravitational interactions can lead to chaotic orbital behavior, mass exchange, or ejection of one component. These dynamics showcase the influence of ultra-dense objects on their companions and demonstrate how remnants can remain active agents in shaping local stellar neighborhoods over astronomical timescales. Observing cooling stars across the Milky Way allows the construction of precise age maps. By combining temperature, luminosity, and spectral information, researchers can infer the formation history of stellar populations, offering a temporal map of galactic development spanning billions of years. Surface features sometimes form due to localized accretion or magnetic flux concentrations, producing temperature variations and subtle light modulations. These features reveal the interplay between rotation, magnetic fields, and gravity, demonstrating that even dense stellar remnants exhibit complex surface activity over extended timescales. Collisions or close encounters between compact residue can generate exotic stellar outcomes, such as supernova or merged objects with unusual chemical signatures. These rare events contribute to galactic chemical enrichment and exemplify the dramatic consequences of interactions between dense stars, highlighting their continuing influence long after nuclear fusion has ceased. The distribution of these residue across the galaxy offers insight into stellar evolution, galactic dynamics, and mass recycling. Their presence marks the endpoints of millions of progenitor stars, while their residual light, magnetic activity, and interactions with surrounding matter continue to shape the structure and history of the cosmos in subtle but measurable ways. Dense stellar cores can retain traces of planetary debris long after fusion ceases, creating thin disks of dust that glow faintly in infrared. Observing these structures provides clues about destroyed exoplanets, asteroid collisions, and the enduring gravitational influence of a collapsed star on its former planetary system. Extreme gravity compresses matter so tightly that atomic orbitals overlap, producing pressure-broadened spectral lines. These features allow astronomers to measure mass and surface density accurately, offering a rare glimpse into how quantum mechanics governs macroscopic celestial objects under extraordinary conditions. Localized magnetic hotspots can accelerate charged particles, producing pulsating light as the star rotates. These bright points reveal internal magnetic structure and rotational dynamics, allowing observers to map features otherwise hidden beneath the dense surface layers of an ultra-compact stellar core. Some cores host crystalline interiors, where carbon and oxygen atoms have locked into solid lattices. This gradual crystallization releases latent heat, slowing the cooling of the star over billions of years, turning it into a slowly fading, diamond-like object suspended in space. Fast-spinning cores may complete a rotation in just minutes, creating equatorial bulges and surface temperature variations. These shape distortions influence emitted light patterns and provide evidence of conserved angular momentum from the progenitor star, revealing how rotation affects structure even under extreme density. Binary interactions occasionally trigger surface flares when accreted material ignites in brief nuclear flashes. These outbursts illuminate surrounding space and produce subtle X-ray emissions, showing the delicate balance between incoming matter, gravity, and the intense pressure of the dense core. Observations in ultraviolet light reveal that younger stellar cores can radiate more energy than the Sun, despite their tiny size, ionizing nearby gas clouds and creating glowing nebulae that trace the final stages of stellar evolution. Thin helium atmospheres overlaying heavier carbon-oxygen interiors influence spectral lines, allowing scientists to reconstruct internal layering. These chemical patterns reveal past evolutionary stages, residual fusion processes, and interactions with captured material from orbiting debris. Occasionally, tiny asteroids survive gravitational disruption, orbiting the compact core for billions of years. Spectral signatures from accreted metals like iron, calcium, and magnesium reveal this ongoing interaction, offering a window into the survival of planetary material after stellar death. Infrared surveys sometimes detect faint, cold emissions from the surface and surrounding dust disks, highlighting the final cooling stages of an ultra-dense star. These subtle signatures allow astronomers to measure temperature, age, and remaining thermal energy with remarkable precision. High surface gravity bends light noticeably, producing gravitational redshift that shifts spectral lines toward longer wavelengths. Measuring this effect validates predictions of general relativity and demonstrates how concentrated mass affects spacetime in measurable ways. Surface temperature inhomogeneities emerge when magnetic poles concentrate energy, creating bright spots that rotate with the star. These periodic light fluctuations provide observational evidence of magnetic structure, rotation, and heat redistribution on the stellar surface. Occasional collisions with planetary debris trigger small flares and transient brightening, illuminating surrounding material. These interactions demonstrate the long-term gravitational influence on nearby matter, revealing how compact cores remain active participants in their local cosmic environment. Crystallization within the core modifies thermal conduction, subtly altering cooling rates. Studying this process helps astronomers estimate ages of older stars and reconstruct the thermal history of ultra-dense objects with extraordinary longevity. Binary companions can induce tidal distortions, causing orbital shifts, mass transfer, and rotational changes. Observing these effects offers insights into gravitational dynamics, angular momentum conservation, and the subtle influence of a dense star on nearby objects over billions of years. Residual heat gradually escapes, sustaining faint ultraviolet and optical emission for billions of years. This energy maintains ionization in surrounding gas clouds, producing faint nebulae that record past stellar activity long after nuclear fusion has ceased. Cyclotron radiation arises when charged particles spiral along strong magnetic fields, producing narrow spectral features. Monitoring these emissions allows astronomers to reconstruct the field's geometry, intensity, and influence on surface plasma behavior in ultra-dense environments. Rapid rotation combined with strong magnetism occasionally triggers surface jets or localized brightening, revealing the interplay between magnetic flux, angular momentum, and energy distribution in high-gravity conditions. Observations of cooling stars across the galactic disk provide a chronological map of stellar populations. Luminosity, temperature, and spectral composition allow researchers to estimate the ages of various clusters, tracing galactic evolution and the timing of star formation events. Interactions with surrounding gas and debris disks influence surface composition and temperature over long timescales. These subtle, cumulative effects provide a record of environmental history, accretion events, and gravitational interactions, preserving the dynamic narrative of a star's final evolutionary stages. Extreme density in these compact stars compresses matter to levels where electrons provide the main resistance to gravity, creating conditions where ordinary atomic structures are altered and quantum mechanics governs macroscopic behavior, offering an unparalleled natural laboratory for studying physics under conditions far beyond terrestrial capabilities. Some stellar cores maintain thin, layered atmospheres where helium floats above heavier carbon-oxygen interiors. These stratifications produce unique spectral features, revealing the chemical legacy of nuclear fusion and accretion events, allowing astronomers to reconstruct the history of both the star itself and material it has captured from its surroundings. Strong magnetic fields can form polar hotspots, where infalling charged particles release bursts of ultraviolet or X-ray light. These concentrated emissions rotate with the star, creating subtle, periodic variations that allow observers to map field geometry surface composition, and rotational dynamics with remarkable precision. Crystalline lattices can form in cores over billions of years, as carbon and oxygen atoms arrange into solid structures. This slow transformation releases latent heat, delaying cooling and producing dense stars that retain observable luminosity far longer than classical models predict, serving as cosmic timekeepers for galactic history. Rapid rotation sometimes generates equatorial bulges, redistributing surface gravity and influencing temperature distribution. These distortions produce measurable differences in emitted light, providing insights into the conservation of angular momentum and the physical response of matter under extreme gravitational pressure. Accreted material from disrupted planetary bodies occasionally ignites in localized nuclear flashes, causing brief brightening events. These eruptions reveal the delicate balance between accumulated mass, surface gravity, and degenerate matter, illustrating the dynamic interplay between external matter and ultra-dense stellar interiors. Observations in ultraviolet and optical wavelengths show that younger cores can outshine the Sun, despite their small size, ionizing surrounding gas clouds and producing faint nebulae that illuminate past stellar activity and provide a record of environmental influence in nearby interstellar space. Tiny asteroids and planetary fragments can survive gravitational disruption, orbiting in stable disks. Spectroscopic analysis of metals such as magnesium, silicon, and iron in these atmospheres reveals evidence of long-past planetary systems, offering a unique window into the survival and destruction of exoplanetary material. Cooling rates are slowed when latent heat is released from crystallization or residual thermal energy. Measuring these subtle temperature changes allows astronomers to estimate the age of ultra-dense stars with remarkable accuracy, constructing a timeline of stellar evolution and galactic development over billions of years. Gravitational redshift at the surface shifts emitted light toward longer wavelengths, confirming predictions of general relativity. This effect provides a direct measurement of mass-to-radius ratios, demonstrating how concentrated mass curves spacetime and influences photons attempting to escape from extreme gravity. Surface convection zones can develop in cooler stars, moving energy through thin outer layers and producing faint variations in brightness. These subtle currents reveal how heat is redistributed under intense gravity, offering insight into the interaction between atmospheric dynamics and degenerate matter. Collisions with orbiting debris occasionally produce short-lived flares, illuminating surrounding dust and gas. These interactions demonstrate the long-term gravitational influence on neighboring material, revealing how compact stellar cores remain active participants in their local environments even after nuclear fusion ceases. Cyclotron emissions arise when charged particles spiral along magnetic field lines, producing narrow spectral features detectable in optical or infrared bands. Observing these signals allows astronomers to reconstruct magnetic field strength, orientation, and complexity, offering a rare glimpse into magnetism under ultra-dense conditions. Binary interactions can generate tidal distortions, redistributing angular momentum and producing subtle changes in rotation or orbital dynamics. These effects offer measurable evidence of gravitational influence over nearby stars and allow reconstruction of long-term stellar evolution within multiple star systems. Infrared observations reveal cold disks of dust from destroyed minor planets. These structures are illuminated faintly by residual thermal emission, highlighting how gravitational forces continue to shape circumstellar environments long after nuclear fusion has ended. Pulsations caused by gravity waves moving through dense interiors produce periodic brightness variations. These oscillations act as stellar seismographs, revealing internal layering, composition gradients, and the extent of crystallization, offering an indirect method to study properties hidden beneath the dense outer layers. Surface temperature inhomogeneities can arise from localized magnetic activity, accreted material, or rotation. These variations create faint, observable bands or spots, providing a visual record of interactions between gravity, magnetism, and matter under extreme density. High-speed rotation combined with magnetic fields sometimes produces jets or localized bright regions, highlighting energy transfer along magnetic flux lines. These phenomena reveal how rotational and magnetic forces interact in compact stars, shaping surface features and emissions. Observing cooling stars across galactic populations allows scientists to construct age distributions and track the history of star formation. Luminosity, temperature, and spectral composition measurements provide a window into the evolution of clusters, the galactic halo, and the timing of past stellar generations. As our journey through the glowing cores of white dwarfs comes to a close, allow yourself to sink even deeper into relaxation. Feel the calm vastness of space wrap around you, the gentle twinkle of distant stars reflecting softly within your mind. Let your thoughts drift like stardust, your muscles soften, and your breath flow naturally and effortlessly. Rest here, fully supported in this safe and serene cosmic space. If you enjoyed this relaxing moment, please consider leaving a like, subscribing, and turn on all notifications so you don't miss any of our future videos. But for now, let your body relax, release any tension, and allow your mind to drift. Good night and sleep well.